Hi, in this video we'll learn what is horizontal asymptote and how we find a horizontal asymptote for a rational function. Let me start with the definition. Horizontal asymptote is a line. So a line y equal a constant. It's a horizontal asymptote of a function if when you find limit of the function as x goes to plus infinity or limit of the function as x goes to negative infinity, either of these guys gives you L. That's the definition. What it means is that, well, whenever you have a limit at infinity, that defines a horizontal asymptote. How does it look like, the graph? How does it look like? Well, the graph of function around the asymptotic horizontal asymptote is something like this. So let me say this is y equal to L. We will have at least three forms for each side. Either function goes like this, gets close and close from above, or it gets close and close. It can be something like this. It can get something crazy like touches, intercepts, and each time gets closer and closer to the line. And also similarly on the negative side. So let me just do one more at least for the negative side. So y equal to L. Oh, well, we can do all three here. On the negative side, as x, oops, well, that's all right. As x goes to negative infinity, this gets closer and closer to L, or it can be something crazy like that, or as if we had. So it intercepts and it gets closer and closer to y equal to L. One thing that is very important remark here is that while every function can have at most two horizontal asymptotes. Why? Because every limit at infinity in plus infinity or negative infinity can give you at most one horizontal asymptote. So every function can at most have two horizontal asymptotes, and to find the horizontal asymptotes, to find them, we find limit of f of x as x goes to plus infinity and limit of f of x as x goes to negative infinity. If it is a number, that number y equal to that number gives us the horizontal asymptote. Let me do one example before we say more words about horizontal asymptote of rational functions. Let's do find horizontal asymptotes of function f of x equal to 2x plus 1 over x minus 3. Well, to find horizontal asymptotes, you have to check two limits. What is limit of the function as x goes to plus infinity? And what is the limit of the function as x goes to negative infinity. And we have learned in the previous video that you can find such limit at infinities by factoring out the highest power of x in the numerator and highest power of x in the denominator. You cancel then x's, what you factor out. Now you have limit of 2 plus 1 over x and 1 minus 3 over x as x goes to plus infinity. Well, this guy is 2 plus 0, 1 minus 0, and that gives you 2. So we have y equal to 2 as horizontal asymptote. How about the other one? Well, the similar computation uh, gives us y equal to 2, and that means that f of x has one horizontal asymptote, which is y equal to 2. While finding limit at infinity plus infinity minus infinity in a special case of rational function is very easy. So let's just write it horizontal uh, asymptotes for rational functions. Okay, so what is rational function? Let f of x be a rational function. Means that you have a fraction of two rational function where two polynomial where p and q are polynomials. Then we have three different cases. One, the degree of p is bigger than degree of q, or degree of p is equal to degree of q, or degree of p is less than degree of q. These are three possibilities for when it comes to horizontal asymptotes of rational functions. If the degree of numerator is bigger than degree of denominator, then there is no horizontal asymptotes. Degree of the numerator, if it is bigger than, then there is no. If the degrees are the same thing, there is only one horizontal asymptote. And how do we get it? Well, y equals to the leading coefficient of numerator over leading coefficient of the denominator. What does leading coefficient mean? Leading coefficient is the coefficient of the highest power of x in the polynomial. So note that the leading coefficient of a polynomial is the coefficient, not the term coefficient of the highest power highest power of x. So you pick the coefficient of highest power of x in the numerator, highest power of x in the denominator, divide them, that gives you a number. Y equal to that number is the horizontal asymptote. And if the degree of the numerator is less than degree of the denominator, then there exists only one horizontal asymptote, which is y equals to 0. So the degree of the denominator is bigger, strictly bigger, then there's exactly one one horizontal asymptote. Let us do a few examples before I move on. We finish this video. Find the horizontal asymptotes. Horizontal asymptotes. First one is f of x is x squared minus 2x plus 5 over 3x cubed minus 1. The second one is f of x is x to the power 4 plus 1 over x 2x minus 1. And the third one is f of x is equal to 3x squared minus x plus 10 over 2x squared plus x minus 1. Okay, so look at these guys. All three of them are rational function. And we have to check what is the degree of the numerator. Degree of numerator is 2. Degree of the denominator is 3. And the degree of the denominator is bigger than, that means that y equal to 0 is the only horizontal asymptote. How about here? Then we check degree of numerator, which is 4, degree of denominator, which is 1. Degree of numerator is bigger than degree of the denominator, then there is no horizontal asymptote. And in the last one, the degree of numerator is 2. Degree of the denominator is also 2. So these are same. That means that we have one horizontal asymptote, which is find the coefficient of highest power of x. So this is the highest power, the coefficient is 3. And find the coefficient of highest power of x in the denominator, that is 2. Y equal to 3 over 2 is the only horizontal asymptote. Well, we started with the definition, and then how does the graph look like for the when function has horizontal asymptote. Then what we did was uh, uh, for the rational function specifically, we have a recipe, very nice recipe, which gives you the horizontal asymptotes of the function.